So our first talk of the session is going to be on estimation of standard auction models.
Thanks for the introduction. I'm Andrew. I'm going to be presenting on estimation of standard auction models, and this is joint work with Yeshwanth and Manolis at Berkeley and my advisor, Kostas, at MIT. Okay, so the problem we're considering is pretty simple. We're an external observer watching a repeated auction. And for simplicity, we'll assume that the auction has a single item. It's memoryless. We're just watching the same auction over and over again. And we know the number of bidders, K. For each auction, though, we don't actually observe all of the bids. Instead, what we observe is who won the auction and how much they paid for the item. And this could be a first or second price auction. So this captures a variety of settings. We could be watching a sealed bid auction where the auction house just announces who won and how much they paid afterwards. We could be watching a Dutch auction. The setting is pretty general. And our goal in this setting, is to estimate the value distribution of all of the bidders participating in this auction. And we'll make this assumption of independent private values, which basically means that each repeated auction, every bidder has their own bid distribution that stays constant. At each one of the repeated auctions, they draw a value IID from their own distribution. And this has a bunch of applications. So for example, we might want to analyze how our auction is doing or simulate interventions. OK, so I have a little pictorial illustration of what I just said. We're watching an auction. We know the number of bidders. We don't see what they bid. Instead, what we see is that agent W won the auction and paid Y dollars. OK, so why is this an interesting problem? Or why isn't this just trivial? Why can't I just watch this auction a whole bunch of times and take the times where agent A won and estimate?
I'm sorry, I have a clarifying question.
Yes.
Do you observe the number of bidders?
You know the number of bidders.
Okay.
Yeah, that's a great question. OK, so the reason I can't just observe this auction a bunch of times, stratify the bidders, and estimate each person's value distribution separately is because my sampling mechanism here is biased. I'm only going to observe agent I's bid when agent I won the auction. And so I'm going to systematically undersample low bids. So for example, on the right here, I have a 2-agent auction where the agents are bimodal and bid either 0 or a value. And in the distribution of actual observed bids, I'm very rarely going to observe the case where a 0 bid wins the auction. The second challenge is converting bid distributions, which is what we actually observe, into values. So our paper tackles first and second price auctions. For second price auctions, we assume that we're at a truthful equilibrium, and so we're actually done. Bid distributions are good enough. For a first price auction, we're going to assume that we're at a unique Bayes-Nash equilibrium, and so we want to go beyond bid distributions and estimate the actual agent's values. Yeah, and so our goal here is going to be estimation, making minimal assumptions about the bidders themselves. So we don't want to make parametric assumptions. We'll try to avoid assuming smoothness or Lipschitzness of densities or things like that. OK, yes?
You do assume a structured estimation that people who bid their Bayes-Nash equilibrium?
Yes, yes. Oh, sorry. Yeah. So the question was, we are making the assumption that in the first price case, they're bidding at a unique Bayes-Nash equilibrium. Yes, we make that assumption. We just want to avoid making assumptions on the distributions themselves. So before I get started with our own work, I wanted to just sort of give an idea of what the landscape of existing work looks like here. So we know, for example, that the value distributions are identifiable from the information we have. There's this paper from 2001 from Athy and Hale that shows that the information we have is, in a sense, enough to identify all of the agent's value distributions. There are also finite sample algorithms if we are willing to make parametric assumptions about the bidders, which we're going to try to avoid, or if we observe all bids instead of just the winning bid. There are also finite sample algorithms for that. Maybe most related is if we're willing to assume that all bidders actually have the same value distributions for the item, then there's this algorithm from Menzel and Morganti that allows us to recover what that value distribution is. But in the specific cases we consider, first and second price auctions, this seems to be it simplifies matters a lot. And then finally, an observation model that I'm going to return back to at a later slide is this partial observation model from Bloom, Mansour, and Morgenstern, where basically we don't even observe the price that the winner paid. We just observe the winner, but we are allowed to set a reserve price for the auction, or we're allowed to insert bids. Okay, this is the most text-dense slide I have, I promise. And now I'm going to jump into what our actual results are. So we'll start with the first price auction case. In this case, again, what we have are, we'll start with just estimating bid distribution. So we won't worry about values for now. We'll assume that each agent has a bid distribution, capital Fi, that's supported on some interval 0, 1. And we'll assume this extra condition that is sort of like a lower bound on the density of these bid distributions. And we'll get rid of this assumption later. But for now, we need it. Again, we assume at each repeated auction, every agent samples some bid from their own bid distribution and bids it. And what we observe are the winner of the auction, which is like the argmax of all of these bids, and what that bid was, which is just the max over all the bids. And the question is whether we can estimate the bid distributions from these observations. And so our first result is just that we can actually do this. So if we're willing to pay an exponential in number of agents sample complexity, then we can estimate all of the bid distributions in Wasserstein distance, which is just some statistical notion of distance. OK, so we might not be super happy about paying something that looks like epsilon to the k, where like k is the number of agents, because that's going to grow really fast in the number of agents. So the question is, can we do better than this exponential? Can we do better than this exponential sample complexity? And it turns out there's a really good reason why we can't. So if you just think about the case where every single agent bids according to like the uniform distribution over the interval, and then we just think about the interval like 0 to epsilon, and trying to estimate bid distributions over that interval, we're going to observe winning bids in that interval with probability epsilon to the k. So with like vanishingly small probability. And so if we're not willing to observe an exponential number of samples from the auction, we're just never going to observe anything in the interval 0 to epsilon, and we won't be able to do anything. And so we can take this intuition and turn it into an actual lower bound, but the point is that we can't really hope to do any better than this. So what we do instead in our paper is we think about something called the effective support of the bidders. And so in this case, we say, OK, maybe the problem is that I'm asking for too much when I estimate over the whole interval 0, 1. Instead, I'm going to estimate over an interval that could realistically be winning bids. And this is what's called the effective support. So I have the formal definition here. It's just an interval from p to 1, where the probability of the winning bid falling below p is at least some constant gamma. And intuitively, the way to think about this is that I only care about estimating the bid distributions for values of x that could realistically be winning bids with some constant probability. OK, once we've relaxed our goals from estimating the full support to just this partial support, the assumption of having a lower bound on the density we no longer need. And it turns out that the exact same algorithm that we used in the full support setting actually gives us an efficient algorithm for the effective support setting. And so we don't need to change the algorithm at all, but now we're paying logarithmic in the number of agents and polynomial in the precision. And we're able to recover the bid distributions under an even stronger notion of statistical distance. OK, the majority of the algorithms in our paper are way too long to fit on a slide, but the first price bid recovery one is not. So I thought I would try to give an intuition for how it works. And then I'll go back to talking about results. So to explain how it works, I'm first going to define two distributions. The first of these is capital H sub I. And capital H sub I, I'm just going to define as the probability. This is like the CDF of a distribution. And I'm going to define it as the probability that the winning bid is below Z, and agent I wins the auction. So this isn't actually a CDF, because like when you evaluate it at 1, you don't get 1. But like if you renormalize it, it's a CDF. And we'll think about it as a CDF for now. The other distribution is just H of Z. And this is going to be just the CDF of the winning bid. So it's the probability that the winning bid is less than Z. And using just these two things, we'll show that you can write down a closed form for the bid distribution of every agent just in terms of these functions. Cool. So we'll start by writing down the density of H sub I. So this is, again, the density that the winning bid is going to be Z. And the rest of the bids, like basically we need I to bid Z. And then we need the rest of the bidders to bid less than Z. So this is going to look like the density lowercase f sub I at Z times like the CDF of the rest of the bidders that aren't I. OK, so that's our starting point. We'll rearrange it in a pretty simple way. Just divide both sides by this product of CDFs. And then we'll divide again by the CDF of just the agent I. So what we end up with here on the left-hand side is something that looks like H sub I divided by this product of all of the agent CDFs. And on the right-hand side, we have a quotient of the bidder's density and their CDF. And so if we look at each side of this equation separately, on the left-hand side, this denominator is just capital H of Z, which is this thing I defined earlier, just the probability that the winning bid is less than Z. And the right-hand side is just, I guess, the derivative of log F. And this is just like standard differentiation stuff. And so this is just like a differential equation. I can solve it. It's pretty easy to solve. Rearranging will just give me this closed form for capital F sub I that's going to be the basis of our estimation algorithm. OK, the last step I want to show is just how do we turn this closed form for capital F sub I into an actual estimation algorithm. And this is a little less important, but basically we can turn this integral into an integral with respect to the measure hi, which basically lets us write our capital F sub I as like an exponent of some expectation that we can estimate. And then the rest of our algorithm is just about arguing that like this expectation will concentrate and give you the thing that you actually want. OK, so now I'm going to go back to results. That's it for that's all the proof sketching I can do. OK, so I want to go back to this partial observation setting that I talked about a few slides ago, where so far everything I've said, we've observed the winner and the winning bid. What if we only observe the winner, but we're allowed to insert bids into each auction, or equivalently like set a reserve price? And we know when the reserve price is triggered. In this setting, this paper from Blum, Mansour, and Morgenstern shows that we can estimate the value distributions paying polynomially in both the number of agents, and the Lipschitz constant of the capital F sub i's. The nice thing about our algorithm, even though it's not really designed for this setting, we can pretty easily adapt it by including like a binary search step so that it works for this setting, and we only have to pay linearly in the number of agents and logarithmically in the Lipschitz constant of the capital F sub i's. OK, the last thing I want to talk about for first price auctions is how do we go from these bid distributions to values. And I'm going to gloss over this a lot, but the essence is that we're going to assume, again, this independent private values assumption where every agent has their own value distribution, and they sample from it IID at each step. And we're going to add this assumption, just for the sake of value estimation, that the agents are at a unique Bayes-Nash equilibrium. So they're all playing their best response to the rest of the bidders. And so I guess I just wanted to make the point that estimating the capital FIs, we don't need to make any structural, like we don't need to make any assumptions about whether the agents are at equilibrium. It's just like a standard statistical estimation algorithm. The part where the equilibrium assumption comes in is just in trying to recover value distributions from these bid distributions. And so our result here is basically that by paying an extra polynomial factor in both the number of agents and one of the parameters of the problem, we can actually recover the value distributions in Levy distance, which is actually good enough to do like counterfactuals with and stuff, which is nice. OK, the last result I want to talk about is moving to the second price case. So for the second price case, again, we have a very similar setup to the first price case. We have a bunch of non-parametric, like we don't want to make any parametric assumptions. We have a bunch of arbitrary distributions Fi over the interval 0, 1. And we're going to make the extra assumption that the CDFs of these distributions, or sorry, the densities of these distributions are both upper and lower bounded by some constants. And in this case, we don't observe the max bid and the max bidder. We observe the max bidder, but instead of the max bid, we observe the second price. So we observe the price that they actually paid. And in this setting, again, we show that over the whole interval 0, 1, we can actually recover the CDFs of all of the bidders under this pretty strong notion of statistical distance. The problem is that we're paying a really, really bad sample complexity. And so one open problem that we want to think about is how do we make a similar sort of effective support assumption or like effective support goal and solve that efficiently? And we don't have anything for that setting yet. Am I doing OK on time? 2 minutes. OK. Great. So in that case, I will just summarize and then point out a couple of next steps. So for first price auctions, what I showed here was how to recover both the bid distributions and the value distributions, assuming we know the number of agents and they all have like this independent private values assumption over both full, inefficiently, and effective, efficiently supports. We also showed how we can use this algorithm. We can repurpose it in a different setting to get more efficient algorithms for this partially observed setting. And in the second price case, again, we get bid and I guess equivalently value distributions over the full support. And something I didn't have the time to show in this presentation is if we want to make the same sort of partial observability assumption that we made in the first price case, where like we only observe the winner, but we can insert bids, we can actually show that we can get a really simple, efficient algorithm for the second price case. I want to talk about just 2 future directions that I'm sort of excited about. The first is finding an efficient algorithm for the second price case by narrowing our scope to just estimating over an effective support. And the second is thinking about more general instances of the setting of like I sample a bunch of people and then I observe their max, or I observe one index that's sort of dependent on the things that I sampled. And the setting is like more generally known in econometrics as self-selection. And we have some preliminary results from linear regression that I'm really happy to talk about offline. The paper is on archive if anyone wants to look, and I'm also available to talk afterwards. That's all.
All right, we have time for a question. Does anyone on Zoom want to ask, or Gather want to ask a question? OK, in that case, I'll open it up to people in the room. Does anyone want to ask a question?
What sort of empirical examples do you have in mind as motivating this work? Is it things like online auctions for ads and things like this?
Yeah, that's exactly it. And like I think to apply it empirically, you might want to relax some of the assumptions about like the value of the item, or like the item itself being constant and stuff like that. But that is the inspiration. There's also some, like a lot of prior work in this setting has studied like the USFS auctions, like the Forestry Service stuff, just because like you can sort of assume that the valuation distributions stay roughly constant. So a lot of the things that assume independent private values have looked at those auctions too.
But I believe in the USFS data, you observe a lot more than you're assuming.
Yes, yeah, exactly.